Hello, I'm excited to present COIL, a framework for cost-optimal interactive learning that is designed for multitask interaction. COIL is designed for human-robot collaboration in factories of the future, which will be semi-automated, collaborative, and fundamentally human-centric. In factories, robots must work alongside humans to perform physical tasks over extended periods. The robot may, of course, ask humans for help, but this must be done while placing minimal burden. Such scenarios are increasingly common in factories, but remain underexplored in robotics research, which currently focuses on partial solutions to subproblems. Existing approaches enable efficient learning of a single task, but are not designed for extended deployment. By contrast, COIL provides an integrated solution that can effectively scale to hundreds of tasks, perform task allocation jointly with interactive learning, and provide strong guarantees on human effort minimization. COIL can decide when to request teaching of new skills, when to assign tasks to the human operator, when to attempt tasks autonomously, and when to request clarification about user preferences. Each of these queries imposes a different level of burden on the human operator and is therefore associated with a distinct cost. For instance, teaching a new manipulation skill is usually the most demanding. COIL accounts for these variations by optimally balancing the trade-off between query cost and expected reward for completing a batch of tasks according to user preferences. Our key insight is to provide a surprising connection between multitask interactive learning and the classical computer science problem of facility location planning. This allows us to compute bounded suboptimal solutions in polynomial time using off-the-shelf algorithms. The facility location problem requires a set of demands to be satisfied by opening facilities, where each facility incurs a cost. Once opened, a facility can satisfy demands by incurring additional service cost. The overall objective is to satisfy all demands while minimizing facility and service costs. In our formulation, we show that multitask interactive learning maps to facility location by viewing the batch of tasks as demands and interactive queries as facilities to be opened. We can also deal with uncertainty in user preferences by requesting the user to clarify their preference whenever appropriate. We evaluated COIL in two simulated domains of grid world and bin packing, and one real-world conveyor domain on batches of up to 30 tasks. Compared with several interactive learning baselines, we found that COIL reduced human effort by 12 to 23% across all these domains, establishing a new state of the art. So, why is COIL so effective? First, by maximizing the decisions for a batch of tasks, COIL takes actions that are globally optimal. In contrast, most existing methods are myopic. Second, COIL can revise human workload on the fly by adapting to failures in teaching. When existing methods encounter a novel object, such as the scan, they typically request teaching immediately to automate the task. On the other hand, COIL anticipates, by planning ahead, that this batch contains more mugs than cans and hence proactively chooses to learn the more useful mug manipulation skill instead. In doing so, it allocates expensive human teaching effort more strategically. However, failures in teaching do happen. Our perception system struggled with this shiny white mug, and COIL responded to this failure by revising its plan on the fly and assigning it to the human operator to complete the task. To summarize, for the first time, we have a theoretically grounded framework COIL for extended human-robot collaboration that also performs well in practice. In the future, humans and robots will work side by side, but humans must always come first. And we will achieve that through algorithms that carefully balance human effort with autonomy. Thank you.